So our next lecture is to think about calculating horizontal and vertical gradients. So we've gone through this idea of how do we calculate and how do we measure total head in a system, but now we actually need to get an understanding of, well, okay, we have two wells, maybe they're adjacent to each other. How is the water moving from in the X or the Y direction, or two wells that are sitting right adjacent to each other? And how is it that they're moving? How's the water moving in that kind of Z or up and down direction itself? This is a key component of what we're trying to do as hydrogeologists. So hydraulic gradient, whether that be in the vertical or the horizontal direction, is the potential direction of water movement based on hydraulic head measured at two or more locations. So what do I mean by that? Let's put in an image. So here is a hill slope, and here's the water table that we can see, the zone of saturation, and here's our water table that we have here. And we could imagine that maybe we have two wells in this environment. So we've drilled these two wells here. So let's go ahead and drill some wells here, and we've drilled a well here. To take a look at the water levels, drill that well a little deeper, right? And now we want to be able to measure the total head in these environments. So we'll first maybe understand what the elevational head is from this reference plane, be able to measure the pressure head by measuring the pressure of the water sitting up here and coming up with total head. We do the same with B, the pressure head, the elevational head. And what we're looking at is the difference, right? So we see that there's some difference in total head between these two different areas. We call that the change in head. So when we're thinking about a hydraulic gradient, we'll take a look at the water level here in A. We'll put H of A here. And moving from left to right across the screen, just like you read, then we're going to go ahead and put B here. So maybe this one was 50, and maybe this one was 40. And then we have some length, and let's say that length is going to be 100. And so we could plug that 100 length in, that's the distance between the two wells. And what we end up with is 10 over 100, right? Or a hydraulic gradient of 0.1. So a horizontal gradient can be derived from wells where the screen intervals are at the same elevation. So in this instance, we may have the screen interval here and we have a screen interval here, and so they're overlapping. And the screen intervals are approximately the same length. Now, the reason that we want to think about these two things is the screen interval, which is going to be the portion of the well that's open to the aquifer and can exchange water with the aquifer itself, means that it's feeling roughly the same zone of pressure, right? And that's why we want them to be roughly the same length and roughly overlapping at the same elevational intervals. Now, vertical gradients can be derived from nested wells where the screen intervals are separated by 1 meter. So here you'll see that here's our screens. We have them here. So each one of these zones here is a screen. Again, a screen you can think of a piece of PVC pipe drilled with tons of little holes in the bottom. That's very similar to what a screen would look like. And we'll take a look at some of those later on. So those are our screens. They're separated. These wells are separated by 1 meter. They don't have overlapping screens, unlike the horizontal wells, because we want to make sure that this well is seeing a different portion of the aquifer than this well. So we want to make sure that they are not overlapping in this instance. And then we can begin to measure the water levels from some datum, and let's put a datum down here, right? And we could measure those water levels and we could take a look here and we could say, okay, well, the water level in B is higher than the water level in A, right? So that means our total head is higher here compared to our total head here, which is lower. So that means that water is going to move from the area of high head to low head. So this is an upward gradient. Conversely, here we could measure it again at maybe a different time, and we see that the total head in the shallower well is higher than the total head in the deeper well, which means that the gradient is in a downward direction. Finally, we can have situations where the gradients in the total head in the two wells is exactly the same. And therefore we have, at least in this condition, no vertical gradient, meaning water is not moving up nor down based on these potentials.